speaker coming to us right out of Florida, actually out of Orlando, Florida. So it's pretty late his time. He's a 10th grade student at Orlando Science High School and has been doing some award-winning research on hive beetles. And hive beetles obviously is a topic that we all are interested here in the Bay Area as well. So he has presented his research to various organizations, got some grant for his research as well. And I'm super excited to introduce Atreya Manaswi tonight. I think we see him on screen already here. He has a presentation tonight here as well. And really looking forward for your presentation tonight, Atreya. I think you should be able to share your deck now. And welcome to Santa Clara tonight here.
Thank you so much. I hope you all can hear me.
Yep, we can hear you well. Thank you.
I'm going to share my slide rack. I hope you can see it as well. Okay. So just to confirm, you all can see this slide rack?
Yeah.
Yes, we can see it.
Thank you. Well, I'm so happy to be with you all here tonight. And so my name is Atreya Manaswi. I'm a 10th grade student from Orlando, Florida. And I've been researching small hive beetles for the past 4 years in affiliation with the University of Florida and also the U.S. Department of Agriculture. So tonight I'd like to speak to you on small hive beetle biology and control, and I'd like to share some of my research that I've done in this field. So before I actually get into my research, I'd like to begin with my backstory of how I really got into honeybee research at a relatively young age. So 4 years ago, I went on a short fishing trip with a friend and his grandfather. Now, while we were on the boat, my friend's grandfather began telling us stories about his beekeeping practices. And keep in mind, he's about 80 years old. So he told us about how decades ago, he would get dozens of barrels of honey, and how that season, he got nearly 3. So this was very, very shocking to me. And I almost remember him describing this tearfully with a very distinct tone in his voice. So I went back home and I dug into the research and the statistics, and I did some brainstorming. And I really came to understand how important bees, and honeybees specifically, are to our economy and agriculture. So I stepped into the University of Florida's honeybee lab in the 7th grade, where I began my first year of research at age 12. So the laboratory is a very comfy and cozy environment where it's air conditioned and there's minimized risk of bee stings or swarming. But as I progressed into field trials in later years, I came to realize the hardships that beekeepers go in the field, through in the field. So that was really eye-opening for me. And it taught me about how hard it is to really put food into our plates. For the presentation tonight, it'll be broken down into 2 main components, the first of which being the biology of the beetle. I'll be covering the background, morphological characteristics, and then behavioral and social characteristics. And the second aspect of this will cover treatment. So this will be twofold mainly. Chemical-based treatment methods and then also organic-based treatment methods. And the research that I conducted with these organizations focused on organic-based treatment methods specifically. So the takeaways I'd like you to have by the end of this presentation are firstly, what small hive beetles are. Secondly, what they do to the colony and the bees specifically, how they interact with the bees and actually cause damage in the hive. Thirdly, what I learned from my research. And then lastly, how you can actually apply my findings into your hobbyist or your commercial beekeeping practices. So let's dive into it. Beginning with the biology, the hive beetle is known as Athena tumida. That's the scientific name, the genus and the species. So this species was actually endemic or native to sub-Saharan Africa prior to the 1990s. However, we saw an introduction of the small hive beetle into the United States in the Carolinas in 1996. And the first official reports came from my home state, Florida, in 1998. So since then, they've spread all across the globe, wreaking significant negative impacts on the beekeeping industry. As you may know, in the States, we manage a very large migratory beekeeping operation with nearly 2/3 of our hives going to California each year for almond pollination. So it's essentially a frenzy. If one hive has a pest or a parasite or a disease, then it will be very easy for that thing to transfer to another hive. And so this is one of the main methods that small hive beetles spread to other colonies through. Now, these beetles, as described in the literature, are very opportunistic and they are smart predators of the honeybee. What they do specifically is they destroy honey and pollen stores and they damage cappings and comb, and this ultimately stresses the colony. Now, this stresses mainly European honeybees or the westernized honeybee, which is what we manage in the States. However, as I mentioned, this beetle is actually endemic to sub-Saharan Africa, where the Africanized honeybee is located. Now, the small hive beetle doesn't really pose a major threat to these Africanized honeybees. In the worst case, it will cause the Africanized honeybees to abscond from the hive, meaning that the bees will just leave the hive entirely. And that can also occur with these European honeybees. But the important point to note is that these European honeybees aren't able to defend as well against the small hive beetle as the African honeybees. So they're more susceptible, are European bees. Now, this is an image of an adult small hive beetle. As you can see on the right, one of these is a male and one of these is a female. So I won't tell you which one is which as of yet, but something interesting you can do with these beetles is you can actually sex them. So I've done this multiple times in the laboratory during research, and essentially what you do is, it's kind of fun. You take the abdomen of the beetle, the very end almost, and then you squeeze. Not too hard, and one of three things can happen. The first thing that can happen is a very long appendage will shoot out. The second thing that can happen is a very short appendage will shoot out or nothing will shoot out at all. And the third thing that can happen is the beetle will simply explode. So assuming you didn't do the third thing and one of those first two things, if that long appendage shoots out, it indicates that this beetle is actually a female. So that long appendage is not a phallus and it's not a male, but rather that long appendage is known as an ovipositor. So an ovipositor is essentially an egg-laying machine gun, and the female uses this to stick that ovipositor into cracks and crevices within the hive, so places that the bees can't actually reach. And that female will stick the ovipositor into those cracks and crevices and start depositing eggs everywhere. This is convenient because the bees can't actually access those eggs and get rid of them, so that makes it suitable for reproduction. And as I mentioned, if nothing shoots out, that's a general rule of thumb, then it's generally a male for the sex. Now, these are some other types of beetles that may show up in your colonies. These two on the left are a pollen beetle and a sap beetle. Now, I underscored these basically to say that just because you see other types of beetles inside your colonies, it doesn't necessarily mean that these are small hive beetles. For example, these beetles at first glance may look like small hive beetles, but you can see this orange pattern contrary to the small hive beetle, which does not have this. And then this sap beetle is much smaller than the small hive beetle. It's 2 to 3 millimeters in length. And the small hive beetle is almost 5 to 6 millimeters in length. So this image on the right is of a large hive beetle. Now, large hive beetles don't belong to a singular species, but rather different regions have their own assortment of large hive beetles. This specific large hive beetle, however, belongs to Africa. And so the large hive beetle gets its name because it's 20 to 23 millimeters in length. As I mentioned, the small hive beetle is 4 to 6 millimeters in length. So this is almost 5 times or 6 times as big, which is why it's called a large hive beetle. Now, I'd like to go over the life cycle for the small hive beetle, and you'll see why this is important. But basically, there's 4 main stages in the life cycle. The first stage is the egg stage. So this is where that female deposits those eggs. And after this, when the eggs hatch, they develop into larvae. So these larvae are actually the root cause of the problem inside the hive. Now, I'll mention this later. But these larvae go through the hive and they start consuming the pollen and the honey, basically, and they defecate inside the colony. Now, after these larvae have consumed their ample quantity of food and they've stuffed themselves, they will exit the hive and pupate in the vicinity of the hive in the soil. So this is what a pupae looks like, this image on the bottom right that's been dug up. And after this pupation stage for 3 to 6 weeks, the beetle will emerge as an adult, and in 24 to 48 hours, it will develop this reddish brown hue. So note here that in good conditions, you can see 2 days for eggs at the minimum threshold if the conditions in the environment are good. So it's 2 days for eggs, 7 days for this larvae, and about 3 weeks for this pupae. So 2 plus 7, yes, give or take a week, plus this third week is 4 weeks. So 4 weeks from this egg stage to the end of this pupae stage. Now, the lifespan of this beetle is 24 weeks. So 4 times 6 is 24, meaning that if conditions are good, you can see up to 6 consecutive generations of this small hive beetle inside your colony. And that really goes to show that if these infestations are not controlled, they can really get out of hand. In fact, these small hive beetle females can lay anywhere from 1,000 to 2,000 eggs, or even upwards in a single life. So they can clearly be a problem if not controlled. So as I mentioned, the larvae are the root cause for the damage. This image in the middle shows a very bad larval infestation. These larvae do appear very suddenly and in large numbers, often in the hundreds or the thousands. Something interesting to note is that there is a yeast associated with the larval feces that causes the fermentation or breakdown of pollen and honey. So as these larvae are tunneling through the colony, they will consume the cappings, the comb, the pollen, and the honey. And once they start doing this, they'll start defecating everywhere. So they'll start releasing feces inside the colony. And so this yeast is what is in that feces. Now, this yeast actually breaks down that sugar inside the pollen and the honey, and this causes the release of a chemical compound called isoamyl acetate. Again, so it's called isoamyl acetate, and the name of this yeast is Codima omeri. So K. omeri causes the breakdown of this pollen and honey and produces isoamyl acetate, which is a chemical. When that chemical is released, and interestingly, that chemical is also the honeybee alarm pheromone. So when that chemical is released, small hive beetles in the vicinity of the hive, actually it serves as a calling signal to them and tells them that there's a surplus of food here. So it's attracting more beetles into that already dying colony. At this stage, which is called a slime out, the brooding will cease entirely and the population will just begin to dwindle. And there's really two telltale signs of a very bad larval infestation, as you can see in this middle image here. The first of which being that when you pop open the lid on a super, you will smell a very rotting citrus and maybe sweet odor. And the second thing is that you will see honey bleeding out from the front of the colony, as you can see in this image on the bottom right. An interesting behavioral phenomenon to note between this honeybee and the small hive beetle is something called a jailing phenomenon. Now, that's not an official scientific term. It's tossed around in the literature. But basically, the honeybees are smart enough to corner these hive beetles into cracks and crevices inside the hive. And so basically, they'll put these beetles into jail cells. This image on the left and in the top right are good illustrations of this. So you can see just a horde of small hive beetles in the top right. And all the beetles have cornered, or all the bees have cornered the beetles into this corner. So this is to control the beetle population. Now, something that can happen 10% of the time only is that the beetles will take their antenna and actually antenate. So they'll start moving their antenna against the mandibles of the honeybee. And so when the beetles antenate with the honeybees, they'll cause the honeybees to regurgitate food. And so it almost looks like the bee is feeding the beetle here, which is actually what's happening. So the beetle has tricked the bee into thinking that this beetle is actually a bee, and the bee is feeding the beetle here. So again, this occurs 10% of the time. The other 90%, the bee is able to pick this up, but that's something interesting to note. And it really goes to show the adaptive mechanisms of this pest and how smart it can really be. Something I'd like to discuss is the distinction between wax moth larvae and also small hive beetle larvae. So here in this image on the left, the image on the top is a wax moth and the image on the bottom is a beetle larvae. One of the most distinctive characteristics, obviously, is that you see webbing and cocoons with these wax moth larvae inside the hive, whereas with these beetles, you see that sliminess, which is termed a slime out. Another big thing is that with these wax moth larvae, you'll see hairs covered all along their bodies. And another big thing, quite literally, is that the wax moth is a lot larger than the small hive beetle. It's double in length and 4 times in width, so it's much, much bigger. Lastly, the wax moth larvae has 4 legs, or 8 legs total here in the back, which are called prolegs, and then 6 legs near the head. Whereas the small hive beetle larvae only has 6 legs, 3 on each side here near the head. One of the other biggest things is this abdominal segmentation you see here. So the small hive beetle larvae has much more pronounced abdominal segmentation, as you can see in this circle. Now, some general good apiary practices for small hive beetle infestations are just when combining or exchanging comb to be careful between the hives, because you can actually introduce small hive beetle's eggs from an outside colony into a new colony that you're trying to put those comb into. Another thing is that when removing old frames or hives, or even adding old frames to new hives, it's important to not use rotten, cracked, and damaged comb. So these dilapidated frames, which will have often cracks and crevices within them, make for very good hiding spots and also spots for reproduction for these beetles. So it's ultimately benefiting them. Now, when pulling honey from the colonies, it's very important to extract as soon as possible, preferably within that 2-day period, because these beetles will remove the wax cappings and start consuming all of the resources inside the hive. And this will ultimately render the honey unsuitable for consumption. So there will be larval feces inside that honey. Now, an easy thing to do, relatively easy, is to expose the hives to sunlight. So the bees do get a little bit aggravated by this, but the hive beetles are completely repelled by this. So this is very irritating to them, and it's a good, very easy way to control for them. The other thing is that with nucleus colonies, or any weak colony that you're trying to add new frames and new supers to, and this also goes for strong colonies, basically giving these beetles more room to move throughout the hive allows them to be more unpatrolled essentially by these bees. So when there's less room inside these hives, the bees are actually able to monitor these beetles in a more organized and a better way. So when you add more supers, these beetles can roam free essentially, and they're able to reproduce more effectively. So only adding as many supers or frames is needed at a time as the colony is growing throughout the season. So now coming to the second part of this presentation with the chemical and the biological treatment agents, I'd like to begin with the chemicals. So there's probably two that you've heard of. These are the most famous, probably. Checkmate, which has a 10% active chromophos ingredient. So this is applied as a strip inside the colonies on the frames. And the second agent is permethrin. So this is Guard Star. It has a 40% active permethrin concentration. And this is applied as a soil drench in the vicinity of the hive. So expanding upon this, chromophos, which is that strip, is applied during stages 1 and 2 of this beetle's life cycle. Now, when it's applied on the frame, and chromophos can actually be used to treat, or checkmate. So checkmate can be used to treat for small hive beetles and also varroa mites. When you're treating for small hive beetles, generally, the strips are cut in half, placed on the cardboard, you staple them, and then place them on top of the frames. When the beetles come in contact with that actual chromophos strip, they'll simply die. That's chromophos, which is checkmate. For permethrin, which is Guard Star, it's applied in stage 5 here, which is the pupation stage. It's applied as a soil drench, so you simply soak the soil in the vicinity of the hive and the larvae will die. Or the pupae, I'm sorry. When the larvae are pupating in the soil, that's what this Guard Star affects. Now, for non-chemical or organic and biological treatment agents, there's quite a few that exist. And one of the biggest probably being attractants. So if you're not familiar with the concept of an attractant, basically, there's traps that can be used, and they're called in-hive traps inside the hive. So these in-hive traps have a solution that's put into them. For example, apple cider vinegar, which has a very distinctive odor, can be placed inside these traps. You're not familiar with this black trap here that I'm referring to, it's called the beetle blaster trap. So there's a lot of these different variations that exist. This specific trap is placed within the frames of the hive. And it's actually what I used in my research, which I'll expand upon further. But basically, the solution is put inside this trap and then placed inside the colony. And what it does is it attracts the beetles from inside the hive into that trap. So it's an attract and kill bait, and that's why it's essentially called an attractant. Once these beetles come in through these slits, and these slits are only big enough so that the beetles can enter, not the bees, they will drown in the solution in the trap. So that's one form of a in-hive trap. This second is a vase board trap. This is diatomaceous earth, the third image. This is also placed in the vicinity of the hive, and it dries out the cuticle of the insect. So this is also an effective control mechanism. This last image here is a nematode. So these types of nematodes, which target the hive beetles, are known as entomopathogenic nematodes. And so that sounds like a mouthful, but basically, these nematodes can enter through an orifice or an opening in the small hive beetle, either through the mouth or the anus, and they will travel through to the gut of the beetle. Inside the gut, they will serve as parasites and start feeding on from the inside of the beetle, eventually killing it. So moving on to my research, there are a lot of existing chemical methods, but there are disadvantages with these and also advantages. So what I wanted to look at was an organic control method that could be very effective. So this is a little schematic that outlines the advantages and disadvantages of chemical treatments, and then also the advantages of the proposed organic solution. So some of the advantages of using pre-existing chemical treatment methods are that these chemical methods are highly effective and they also show fast results. However, there are many disadvantages. So these include the price of these chemicals, which can be very, very high, especially buying at a commercial scale. The second is the risk of soil, water, and environmental contamination. So often these chemicals can leach into the environment. For example, in soil, they have a half-life of 30 days. And in in soil, they have a half-life of up to 1 year. And in water, it can be up to 30 days without sunlight. So they can last for a very long time in the environment. And this can ultimately affect wildlife, aquatic life, humans, and the honeybees themselves. So many reports have also shown that there have been high amounts of chemical residues inside various hive products, such as royal jelly, propolis, wax, comb, honey. These are ultimately things we consume and use in industries such as the pharmaceutical and beauty industries. So they're being used by us in our bodies or on our bodies. The proposed organic treatment solution through the research was shown to be affordable and sustainable, very effective for small hive beetle capture, environmentally friendly, and also it poses no risk to any organisms. So what is this agent and what is this research? This research is broken down into 2 phases. So phase 1 of this research looked at 7 organic and inexpensive small hive beetle treatments. And the second phase, which was year 2 of this project, was looking at developing a novel treatment based on beer. So beer was found of these 7 agents from the first year to be the best agent by far. And so that sounds very interesting, and I'll get into that further. But basically, the second year was looking at refining beer in the form of a chemical solution, basically making an artificial beer blend that was better than beer itself. Let's dive into it. So for phase 1 or year 1, here we were looking at 7 organic agents, and so these were apple cider vinegar, mango puree with boric acid, cantaloupe puree with boric acid, and for reference, both of these purees had a 2% boric acid concentration, serving as a killing agent, the boric acid. There was yeast, baker's yeast, peanut oil, grapeseed oil, and lastly, beer. This list may seem very abstract or arbitrary, but it was actually chosen based on research findings in the literature. So literature has shown that this small hive beetle, which belongs to a class of Coleoptera known as Nidodulidae, can fundamentally feed and reproduce on tree sap, rotting fruits, and such odorous compounds. And so based on this, these odorous or smelly compounds were chosen. Now, this image on the bottom right shows the beetle blaster traps which were used in this research. So each of these treatments was placed inside this trap about halfway, so that's 10 to 12 milliliters of solution. And so this is a mini beetle blaster trap, the 6-inch version. So the solution is put about halfway into this trap. Now, these are some pictures from my research, and I have some fun stories to share. So this is first image of me in the field with the beekeeping equipment. So you might be thinking, what a responsible young beekeeper, right, with his protective equipment. But that's completely incorrect. That'd be a wrong statement. I got stung dozens of times in the field. I lost count so many times, the belly button, on the arms, on the legs. They find a way to get into that suit somehow. So I had a somewhat miserable time the first few times going into the field, and I got stung countless number of times, which is very painful at first. So the second image is of me counting beetles in my mother's kitchen. So I didn't have access to a lab at this time. This was during the pandemic in 2020. So I'd have to take these beetle blaster traps, cut them open, and sometimes these beetles would be alive. So these beetles would start flying around in the household. I remember my brother and I, we'd take fish nets in hand and start trying to capture these beetles. So my mother wasn't all that fond of us counting beetles in my mother's kitchen. But I had to do what I had to do for the sake of science, right? And to this day, there still might be beetles loose in my household. We'll never know. Now, what I would do each week is basically take these beetle blaster traps and place them inside frames within the hive. So if I have an image here to reference, I actually don't here specifically, but basically these frames, there's 10 frames inside each super, and the trap would be placed in between the frame and the hive. So it would be left there for a week, and then after that week, the trap would be taken and then replaced with another treatment. So this whole trial was run with 24 honeybee colonies, and so it was run over a 6-week period. So it was a very extensive field trial with a lot of data collection. There were 290 samples throughout the course of this 6-week period. So a very, very extensive field trial that was comprehensive. And each week, these traps would be put into the hives, extracted, and then replaced. And so they were replaced according to a randomized schedule. And so a randomized schedule was used to account for the varying levels of the beetle populations in each colony. Now, I don't want to dive too much into this, but basically these are the statistics for this project. And what's important to note here about this table is that the treatments are being compared against one another. So, and what's being compared actually is apple cider and another treatment. So apple cider, which is a very common and popular agent for small hive beetle capture amongst beekeepers, was used as the control of this study, basically the baseline. So apple cider was compared against mango, apple cider was compared against cantaloupe, it was compared against yeast, peanut oil, etc. And so basically we were looking to see if another treatment in the study was better than this baseline. And all of these columns with these orange arrows are the treatments that were better than apple cider. So mango was shown to be better than apple cider throughout the course of the 6 weeks. Cantaloupe was shown to be better. Yeast was better and beer was better. So these 4 treatments were shown to be better in capturing beetles than apple cider. Now, which one is actually the most effective? That was a question to be asked after that analysis. And so another test was run to figure out which of these treatments is actually the best out of all of these 7 agents. And so beer was by far shown to be the most effective, which you can see in this bottom right chart. All of these bolded numbers are for beer. And so that showed that beer was very, very effective by far. Looking at this graphically and moving away from those numbers, you can see beer here in deep blue. So beer has a total beetle capture of 198 throughout the course of the 6-week period. And these are just the bars for each of the treatments you can see. Apple cider here is at 11 in this other blue color. But what's special about this specific Pareto chart is something called an 80-20 rule. It basically states that if you take this 80% mark, trace the cross horizontally and then down, this segment towards the left, 20% of that segment on the left accounts for 80% of the entire population. So I'd like to reiterate. Here on the left of this red line, here, these 3 bars, 20% of these 3 bars accounts for 80% of all of the beetles captured throughout the course of this entire experiment. And that really shows you the efficacy of beer mostly throughout the course of this study compared to the other agents. Looking at this in another way, this is a box and whisker plot. So this X, which is what I'd like to pay attention to, please, is the mean for this beer. So you can see this X, which is the mean or average, is much higher than any of the other X's for the other treatments, meaning that beer had a much greater consistency and efficacy throughout the course of the 6-week study in its beetle counts. So ultimately, the findings from phase 1 or year 1 were that beer was 33 times more effective in beetle capture than apple cider vinegar, and it was the best treatment by a large margin. Moreover, beer costs nearly 5 cents per hive on average, and it's also widely and readily available. In addition, beer does not harm the bees and only the beetles, so I guarantee you'll not have any drunk bees using this inside your hive, even if it tips over, which it's not likely to do. So this is what it looks like inside the hive. The beetle blaster trap is placed in between these frames, and so it will not tip unless the whole hive is actually knocked over. Now, if you didn't believe me about how cheap beer actually is, this is just an image from Walmart.com. So you can see Miller High Life, which is the beer that I use, and Miller was used because it's inexpensive and readily available. Miller here costs 7.3 cents per fluid ounce, compared to apple cider vinegar, which is nearly 20 cents. So apple cider vinegar was 3 times as expensive and also 33 times less effective. So beer is better in both ways. Now moving on to phase 2, which was the treatment invented essentially. This is looking at developing a beer blend based on beer's chemical composition. So the goal here was to refine beer in the form of a more concentrated solution. And so if you don't know, beer is 90 to 95% water, so it's very, very diluted. And the idea here was that if you could concentrate beer in a pure form without all of that water and other unnecessary chemical compounds, it could be much more attractive to the beetle. So there were two goals of this study. The first was to make this beer blend even cheaper than beer itself. And the second was to make this beer blend even more effective than beer itself. So those are the two goals. So how did I actually go about doing this? The first step in this process was extracting the chemicals from the beer itself. And so you can see this white tube here. And so this is known as 10-TA. And so this is called a polymer, basically. And this is a vacuum here, this black box. It's connected to a tube. And so when this vacuum is turned on, the air is pulled from this beer bottle, and it's trapped inside this white tube. And so the chemicals are stored inside that container. The chemical structure of that polymer is such that the chemicals inside the beer are trapped in it. So all the chemicals from beer are inside that white tube. And so this was done for 15 different samples, so 15 of these tubes. These tubes with the chemicals of beer were then placed inside this instrument here in the middle, which is called a GCMS. And so that's a gas chromatography mass spectrum. Again, a very big, unnecessary word that's a mouthful. But basically, what this machine does is, once you put this sample in, it heats the sample to a very, very high temperature. And this causes the release of these chemical compounds inside this white tube. And when those compounds are released, they're introduced into a coil inside this machine. So once introduced into the coil, these chemicals begin to separate based on their molecular weight. Now, this coil can be 10 meters to 100 meters in length, so it's very, very long. And at the end of this coil is a detector. So once these chemicals start separating, obviously the lighter chemicals move faster through this tube, and the heavier chemicals begin to slow down. And the lighter chemicals will come to that detector first at the end of the coil. So this machine also produces a reading. So this reading is shown on the right. On the x-axis, this bottom axis, you can see time in minutes. So the more left it is, the quicker it's showing up. These spikes are chemicals that have been identified. So for example, this spike here on the left, this is where I have my cursor, is the first chemical that was picked up, and it's the lightest compound in the sample likely. So this is important, and these chemicals are actually analyzed because it's the lighter compounds that were actually of concern inside this study. Because these lighter compounds are actually what are carried through the air more easily, and thus they're picked up by the beetle first. So for example, if you have a heavier compound and a lighter compound, this heavier compound will sink in the air, and the lighter compound is more likely to rise and be carried. So that lighter compound will be picked up by the antenna of the beetle. So it was these lighter compounds that were identified, and 4 specific light compounds were picked. Now, these compounds were tested in a EAG, which is an electroantennagraphy, another mouthful. But basically, this EAG is where the antenna of this beetle are taken. They're excised. So the antenna are removed from the beetle, and they're placed onto an electrode. So this is a very interesting process. As I mentioned earlier, these beetles are 4 to 6 millimeters in length. And so their antenna are a few hundred micrometers. Now, under a microscope, it's still pretty difficult. And it's also like neurosurgery, but on small hive beetles. And it's very tricky at first, but I got used to it after a few tries and a few failures. But after these antennae are extracted, they're actually alive from anywhere to 3 to 5 minutes. So time is really of the essence here. And once these antennae are placed onto that electrode, you can see this filter paper here with this right arrow. So this filter paper has been dipped inside a specific chemical compound, and then it's placed inside this tube. So this filter paper is also attached to another tube that you see running down through here. And that tube is connected to a foot pedal. So when this foot pedal is pressed, air is pushed through that tube, and this air carries the chemical from this filter paper and it introduces it to this antenna. So basically what's happening here, any of that didn't make sense. The antenna is on an electrode, and this antenna is being introduced to chemical compounds. So basically, through this process, you can see how the antenna is responding to specific chemical compounds. And so basically, it's as if you can see how the beetle is reacting to specific chemicals. And so this antenna, which is on an electrode, is connected to a sensor, and this sensor amplifies the readings to a personal computer, which has a graph, and this can be analyzed to see if the response is positive or if it's negative. Now, after this process and seeing the responses of the beetle to specific chemicals, 2 blends were created. There was an oil-based blend and a water-based blend. So these were tested along with beer and also a control. for 8 weeks in 28 different honeybee colonies, so an even larger trial than last year. And so this is about 2 million bees, a very, very large sample size. This image on the right here is of beetles being captured in a beetle blaster trap, and all of these black specks are actually beetles. So this capture is in the hundreds, and so it's a lot. Again, these are statistics. Basically, the oil blend 1, which is the blend based in oil, was shown to be the most effective by far compared to the other treatments. Looking at this graphically, so this is more pleasing. Basically, the oil blend, which is in gray, had a total capture of 620 beetles throughout the course of the 8 weeks, compared to the oil water blend, the second blend, which is 269, beer, which is at 125, and the control. So you can see the oil blend dwarfs beer. And so beer was shown to be so effective in that first year, but the oil blend is much better than that. So again, you can look at this 80-20 rule, 80% here, and then tracing down. So about half of this oil water blend, and then the oil blend, 20% of the oil blend and half of this water blend. 20% of this data on the left counts for 80% of everything. So very, very significant capture for the oil blend and part of the oil water blend. The conclusions from phase 2 were that the oil blend was extremely effective by a far margin, and the 2 research goals were accomplished. The oil blend was shown to be 5 times more effective than beer and also half as expensive as beer. So why can you use my findings and how? Now, unfortunately, this oil blend is not available commercially as of yet, but beer is. So this is currently being worked on with the USDA, but beer can be used inside the colonies, and it does not harm your bees in any way. So you will not get drunk bees again. Beer can be used inside any in-hive trap as an attractant. So anything that requires a treatment solution for the beetles to be attracted, beer can be used inside of it, not just the beetle blaster trap. Beer is also very cost effective, as I highlighted earlier. In this image, again, 7 cents per fluid ounce for beer compared to 20 cents per fluid ounce for apple cider vinegar. So it's 3 times as inexpensive. And the key takeaways I'd like you to have really from this presentation are that it comes down to good apiary practices, having cleanliness, hive exposure, not adding too many supers onto these colonies, exposing your hives to ample sunlight. So that's the first thing. And then the second thing is the use of organic, ultimately, or chemical treatment methods, whichever it comes down to your personal preference to control for these small hive beetle infestations. And so ultimately the synergy of these treatment methods and good apiary practices that reduces the beetle populations to a manageable level and keeps your hives healthy. So these are some resources for small hive beetle management that I can definitely share with Mr. Eshelbeck if you'd like to circulate these amongst you all. So if you'd like to take a look at these are some good resources about the biology and also control methods for these beetles. This last link is of the UF Honeybee Lab. So this has good videos. These are comprehensive on not just small hive beetle management, but just beekeeping practices in general. So that's all I have for you all tonight. Thank you so much for your time and attention. One thing I do request before we open up to a Q&A is if you could all take one moment and maybe possibly pull out your phones and open up your camera to this QR code. I do have a short form which I'd request if you could all fill out. It's just 2 questions asking what you thought about my presentation and my speaking abilities. This would be very, very helpful to me for future presentations. So if you'd like to hold up your phone and fill this out, I greatly appreciate that. So thank you, and now I'm open to questions and answers. So anybody has any questions?
Hey, thank you so much for the awesome presentation. I think we learned a lot about beer tonight. I will be buying some beer tomorrow morning. That's my first job, I guess. But one of the questions I was wondering is, you were talking about the oil blend that is even more effective than beer. Can you share with us what kind of oil blend that would be?
Right. So that specific oil blend was created in a laboratory based on 4 specific chemicals isolated from beer. So unfortunately, that blend, the formula for that is proprietary, and it can't really be created without that specific instrument. But the base of that oil blend was soybean oil. Unfortunately, that blend is currently under a patent process. So if that were to be released commercially, it would be available at a very cheap price. But that's what the USDA is currently looking at with that. So I'd have to update you on that in the future, but beer is probably the best thing, second best thing you can use for small hive beetle capture compared to that oil blend.
Okay,
And
very
again,
helpful.
yeah, of course. So I did use Miller beer, which it's Miller High Life. It's a lager beer. So that's available at Walmart or Publix. So
That's good to know as well. That's super good to know. We have a number of questions here in the room and then maybe some online as well, but let me get started here.
Hi, great presentation. How do you know that when you made the more effective attractant, that you weren't bringing in more beetles than normally would be? And an analogy would be, you have a bar, we're sticking with beer right now. You have a bar that normally has 20 clients, and then the bartender introduces this awesome cheap beer, and the word out in the street gets there, and suddenly you have 100 people in there. And so, and the reason I'm asking this is, if it is true that you are attracting more beetles with it, then I would start to lean towards having bait hives where there's no bees and you just have the attractant in the traps. Thank you.
right. Thank you. So it's a very interesting question. I don't think this attractant, honestly, from just observing it inside the hive and honestly smelling it and just seeing outside the hive how strong the scent really is. It is a very strong scent, but I highly doubt, based on these in-hive traps and the way that they function, that beetles from outside the hive are actually coming. What we're seeing consistently is that there's a high capture of these beetles where this trap is being used. And it's not necessarily at a specific location. At different locations with different environments, we're seeing very high captures with this specific trap, with that solution. So that's a very interesting hypothesis that could be tested further, seeing if you can attract beetles from outside the hive into that original colony. But for that to occur, I think it would have to be a very, very potent scent. So thank you.
Excellent presentation. We have been using the beetle blasters and just putting in vegetable oil, and they seem to go in there and drowned. But after your presentation, I think I will either add beer to the vegetable oil or empty all that out and just go with Miller High Life. Have you tried vegetable oil mixed with beer, or you would just say go straight beer?
That's definitely something you could try out. I haven't tried the combination of both. I have tried both separately. Whatever works for you. I think if you want to try the combination and see what happens, I'd be happy to know and I'd be interested to see what happens with that. But definitely you could see what happens inside probably a strong hive and see how the beetles are responding to that. That'd be very interesting. I think you could definitely just try the High Life. One thing to note is that unfortunately in these higher temperatures, now we're going into a season where these beetles are actually, their populations are going down relatively. But especially in summer, sometimes the beer will evaporate in a matter of a week and a half or 2 weeks compared to these oils. So that is something to note. However, when that blend was created, the oil base was used specifically so that it would last inside that hive for a very long period of time. But that is something to note. So you could definitely test the combination of vegetable oil and the beer and see how that works out. You may need to investigate some emulsifying agents. Basically, the water inside the beer and that oil won't mix very well, so you'll get layers. But if you want to purchase some sort of emulsifying agent, which could be very cheap, it would help mix the two. So you could experiment with that a little bit and run your own trial, I guess.
Right. Thank you very much, because dehydration, possibly, I should say evaporation of the beer. So anyway, that was the oil concept, but thank you very much. You're very helpful.
Of course. Thank you.
Hi, this is John. My question is it the same mechanism that kills the beetles in the beetle blaster? With the oil, I always thought they drowned in there. Do they also just drown in the beer as well? Is that what kills them?
Yes. So they actually can't survive in that. And once they get into that trap, they drown. So the reason that 10 milliliter concentration is used is actually because it's about halfway. So if you fill the trap too little, then you obviously won't get good attraction. But if you fill it up too much, what the beetles can do is, and they're very smart about this, they'll lean into the trap, give a little sip, and then they can dip. However, if you fill it up just about halfway, it's enough so that they lean in and they fall in, and then they drown in the solution, so they can't get out of that. But yes, they do drown.
Hi, this is Helen, and I have a question more about the life cycle of the hive beetle. I have hives that are on a large concrete pad, and I was wondering how close earth needs to be to support the life cycle. I'm always surprised that I have hive beetles, and considering that the hives are on concrete pads. When I say concrete pad, I mean it's a large area that's been concreted over that the hives are stood on.
Mm-hmm. That's very interesting. I have a short story I'll tell you. So I actually work with a professor you might know, Jamie Ellis. So Dr. Ellis, he was actually doing some research in South Africa with some hive beetles. And so in this experiment, he's working with the hive beetles, and one morning he came to the laboratory and he saw these larvae crawling through the hive. The door was left open. They were crawling through the door. They crawled down the stairs and through the door of the building into the soil. They went all the way from that upstairs laboratory. These larvae were crawling down to the outside to pupate in the soil. So they can go very, very far, even through an entire building to try and reach that soil. So there's not a clear-cut answer really for that. And a lot of people have tried concrete slabs or gravel or trying to elevate these hives in some sort of surface. You could try diatomaceous earth. I don't know if you mentioned that, and seeing how effective that is, or trying nematodes to use in the soil. Another good thing to do would try and implement an in-hive trap and see how that would work as well. But that would really be one of the best control mechanisms. Maybe try using a combination of those three and then seeing how that works. But again, they will go and they can crawl a very large distance to try and pupate in that soil.
Thanks very much.
Mhm.
Any other questions? There was another question in the room about what's the time where most of the hive beetles are actually growing or expanding. Is there a seasonality to it, and what would it be?
Yeah, so it's generally you're looking at the spring and then also the fall. So those are really the screen. Okay. Yeah, so it's really the spring, somewhat summer, and then the fall. And the fall is really when they do the best. So yeah, the fall is when you want to implement the most control mechanisms. That's when beetles are normally treated for with these chemical agents, the strips.
Great. Do we have any more questions either online or here in the room?
I think you will become a terrific presenter in the future.
I agree. We've listened to a lot of presenters before, and no offense to any of them, but that was probably one of the best ones I've ever listened to, and I was very engaged, and so great job. Like really, wow.
Yeah.
Thank you so much. That means a lot.
I kept looking. I'm like, are you sure he's in 10th grade? Can't be. You know, are you sure?
Yeah.
Agreed. I was in marketing and you definitely could get a job in my shop.
Oh, I do have one more question. I don't know if you can answer it. So when you say that blended oil is being patented right now, are you doing that? I hope.
No, that's currently the agency that I was working under, the USDA. So we're currently looking into that. Yeah, that process is going on. And this research is also being looked at, putting into a peer-reviewed journal. So hopefully getting that validation through the process of peer review and putting this out there to try and spread the word about this. That would be great. That's what we're looking at doing.
Quick comment on hive beetles. I had some honey stored in a trailer where I had them in large commercial trays like Costco uses and such. And I'd left them for a couple months, and I found hive beetles had gotten in there, and most of the hive beetles were unable to get up the lip and out of those trays. So simply putting a tray under with an inch and a half lip can keep them in.
That's interesting. So the honey stores after that, were you able to deal with that? Because I've heard some people, and I'm not sure how the research deals with this, the research side of it, but some people have tried using peppermint. They'll crush up peppermint candy, place it inside the hive, and that has something to do with like ridding the hive of the beetles. And so they're able to use the honey still after that, once they treat it with the peppermint, I guess. But what happened after that? I'm just curious. They stayed in the hive?
He was feeding it back to the bees, the honey.
Oh, okay. Okay.
You mentioned, extract the honey within 2 days or so. I now freeze my frames because I don't like bugs. So obviously they die then.
Mhm.
Do you recommend everyone freezing their frames?
If you weren't wanting to extract that within like a quick time span, like within that 2-day period, then that would probably be a good idea to try and not get any infestation with that. I'm not familiar with how, like, if you were to freeze, how well the beetles would do, or if they would just die off in that temperature, likely that would happen. I'm not sure how long you can keep it that way, but yeah, that would definitely work if you didn't want to extract immediately.
Next presentation.
And just something to add, I do have a younger brother, right? And so I didn't do a beer comparison study. And a lot of people were asking about that. Like, oh, you did Miller High Life. What about different types of beer? So he's actually working on that this year for a science fair project. And so he's going to be looking at that and seeing what the outcome of that is. So Miller is a contestant in that and a few different types of beer. So it's basically varying on the alcohol by volume concentration, the ABV. And so basically looking at that and seeing how that affects the capture. That'll be interesting. I can definitely share the results with you all on that.
Well, thank you so much, Atreya. You're not only a very talented researcher, you are an excellent speaker and presenter, and we're really super excited about hearing from you tonight. So we're really excited, and we'll certainly following your work, and certainly hopefully that your work will eventually become available as a product down the road that we can all use there. So all the best and continued success for your journey. And do reach out to us anytime. We are here to help and support you. If there's anything we could do to support you, reach out anytime. Thank you.
Thank you. This is a tremendous opportunity. I'm so grateful. I hope you all learned something. Thank you.
All the best. You can stay online if you prefer. We have a few business items to cover, but it's up to you if you want to stay online. Totally up to you.
Okay. Thank you.
Yeah.
Good night.
Tomorrow.
I'm not Roger, as you know, but Roger is traveling. He said he's, I believe, in Europe somewhere traveling. And so I think there is a few more business items that we will cover tonight. One of them is around the upcoming election for the board for next year. And Davey, I think, has prepared a few comments here to give us some insight there.
Per our bylaws, every December we have our potluck meeting, and we usually present a slate, but at any point in time, per the guidelines, people can nominate themselves for different positions for the board. We'll present a slate. If there are other people who are interested in it, reach out to me at my email address, parliamentarian@beagle.com. If you're interested in any org, right? Sorry. If you're interested in any of the position information, they've been added in our newsletter. Go back and review those. And we are, and of course, I've reached out to a few people to see about trying to fill some positions on the slate that might be some big shoes to fill at different points in time. At this point, here right now, I'm interested if anyone's want to nominate someone or themselves. They can do it online, put it in the comments, and or just reach out to me at my email address here online. We'll go do that course of business next time we meet up in December. All right. Dear Hark's gonna come in from the back of the room.
Do you have any other business to cover tonight? If not, then yeah, we are still determining the exact kind of setting for the December meeting. As you know, the December meeting is usually a potluck and the election and many other important things to talk about. This is our last meeting for the year. We could do that here. Okay. So we'll probably decide in the next week or two and then come back with communication. Yeah. I mean, this is a great location. So thanks again to Owen for actually making it available to us. I mean, this is an awesome place here. Thank you. That's even better. But thank you for that. In terms of the December meeting, we should be letting you know in the next 2 weeks in terms of the exact format. But there will be a meeting in December and the format will be TBD. I think that gets me to the last part for tonight, which is our freebies, our gifts to everybody that showed up